Cool. Yeah, let's get started. I will share our presentation. Yeah, so as mentioned, this week we're going over a survey on LLM-based autonomous agents. So this kind of goes over all the latest papers from the last 2-3 years on building agents. So it's really focused on like that and only that, and it covers it across like the entire spectrum of agents that are tuned for different purposes, different domains, and it breaks the entire process down for agent architectures into 4 different sub areas. So these include the profiling module, um, the memory module, the planning module, and the action module. So this is kind of like the main components that any agent needs to have. And it kind of discusses how each paper contributes to one of these areas. So profiling is essentially responsible for setting the role of the agent. So kind of like this is a doctor agent or a developer or et cetera, et cetera, et cetera, and kind of setting its like role or personality and so forth. The memory module is obviously memory, so how it can remember everything it's done, how it remembers the world, actions, all of that. Planning, again, is how it plans based off of its profile and its memory, and then actions, how it actually executes things in its world. Yeah, and then now we'll go into each of them in kind of detail. So this is a diagram of how they break down kind of the entire agent architecture, right? So within the profile, they have like 3 main generation strategies: handcrafting, GPT or LLM generated, and a dataset alignment method. And then you can kind of set it based off of a ton of different profile contents for demographic information, personality information, social information, etc. Memory, there's a few, they decompose it into the memory structure, format, and operations. So within the structure, there's short and long term. And then you can store that memory in various different ways. So you can do it like through natural language, through various embeddings, through more conventional databases and SQL operations, and then structured lists and like dictionaries that preserve the hierarchy of a memory. And then they also decompose into different memory operations. So kind of read, write, reflection, and then memory management as well. So how to like store the top memory, how to delete memory when it's no longer relevant, how to condense memories, how to kind of transfer memories from short to long term, how to synthesize. So there's a lot in this memory section. And also reading and writing is also like not just database operations. You can like, try to, if a memory has changed or if you have like multiple memories about a similar concept, it kind of goes into how to handle that. Yeah, I think this is like a huge area that they're gonna probably be a lot more research in. And then planning, 2 different overall areas: planning with and without feedback. So without feedback, this is kind of like your chain of thought, where you give it a prompt and based off of, or you give it a kind of goal, and then based off of that goal, it comes up with a plan. And there's no real feedback in that plan. It just came up with what it thought. And this also has like, chain of thought. It has tree of thought. External planners. So these are kind of systems that are more like formal planning things. Like they mentioned something called DDP or something. And it can kind of be more related to domains. So if you're doing robotics, you can have like an optimization planner for that environment, or anything else that's like an external planner that's specific to some domain. So yeah, those are kind of all the ones without feedback. And then with feedback, this is when you're trying to like reflect on the planning process. So the environment can give you feedback. You can have different critics that kind of tell you, hey, this planning step was good, wasn't good, is consistent with your memory, is not, etc. And then also model feedback. And then the last one is kind of actions. So there's three main action targets that this paper broke things into. The agent can either be tasked to like complete a dialogue, it can finish a task, or it can kind of explore the environment and find new things to interact with. And then the action strategy. So this is like how it takes the action. It can either recollect past actions it's taken, can interact with the environment, it can get feedback, and it can use external tools. The action space is tools or no tools. And then action influence, yeah, you can be influenced by various different things, including environment, the internal state, new actions that are kind of available to you, and human. So yeah, I thought this was like a pretty nice way of decomposing all of this. So what it does later on in the paper, let me go there quickly. So they also have this kind of a table that kind of goes across a lot of the latest agent papers and kind of decomposes like which ones use which approaches, which I think it's pretty neat in the sense that you can kind of get a sense of if you're looking more at papers that are doing action planning with feedback or anything. It's kind of a very condensed representation of all of that content. Okay, cool. So now we'll try to go through each of them in more detail. Obviously, I think a really nice follow-up would be picking the most interesting of the reference papers and diving a little bit more into them. Hopefully we'll do that like next week or the week after. Okay, so for profiling, there's like three main methods that we mentioned. One was handcrafting. This is essentially where you just use a prompt and you're pretty elaborate about all of the qualities of the agent in that prompt. So generative agents, MetaGPT, ChatDev, self-collaboration, all kind of do this. And it's like pretty much the standard, even what ChatGPT does, I think, is like, you are a blank, you do XYZ. In this situation, you should do that, right? And then the other one is LLM generation method. So here it's like similar, but you have like a few seed agents to serve as few shot examples. And this kind of gives the LLM a template of this is how this should work or how these profiles should be. And then they have some sort of variables upon which it can it can differentiate essentially. So based on those variables, it kind of generates a lot of similar types of profiles. Yeah, so the rec agent is kind of an example that they provide of this. It first creates seed profiles for a few agents with age, gender, personality traits, movie preferences, etc., and then leverages ChatGPT or GPT to generate a wide plethora of like similar profiles. And then the last one they mentioned is data set alignment. So this is like if you have a data set of a lot of socioeconomic data or just profile information saying, hey, this user, this is like a lot of data about this population, XYZ criteria. Can you create a lot of agents that match this data set? So yeah, it's just kind of using that to seed your profiles. Cool, we went over this. So now kind of diving into the meatier parts. The memory module, I think, I still don't think any of these are amazing, right? I think there's still a lot of work to do, but we'll go over kind of what they have. So their main two distinctions in terms of the memory structure is unified or hybrid. So unified is literally you throw everything in one place. No distinction between short and long-term memory. It has a unified interface for reading, writing, and reflection. And all of these papers have a version of unified memory. So Atlas, Augmented, LLM, Voyager, and Chatlog. And there's different ways of accessing it. You can access it via prompts, or kind of querying, etc. But at the end of the day, it's one massive store. And then the hybrid memory clearly differentiates between short and long-term memory. Short-term memory stores the current trajectory, and long-term memory saves reference plans summarized from previous trajectories. So this, I think, the main first paper that came out with this was generative agents, where we can discuss it a little bit more. But the generative agents paper essentially had like steps where it would yeah, I think I have a slide on it. Let's see. Yeah, here. So this one, the memory reflections one's from generative agents. The agent generates 3 questions based on recent memories and uses these to obtain relevant information. And then it generates 5 insights. And then those insights get stored in the long-term memory. So it's essentially, yeah, it's like generating its own reflections. So I had all of this memory logs stored for the last day, and the memory is just like I did XYZ, et cetera, et cetera. And then based on that, it asks it high-level questions like, how are you feeling during this process? Or how was your interaction with this person? Et cetera, et cetera. And those questions are kind of generated based off of your short-term memories. And then the answers to those questions are like, oh, I'm really good friends with Sarah, or I did not feel comfortable at that party, something like that. And then these become like long-term memories or insights that build on the kind of character profile of that agent. So yeah, that's kind of a way that they're able to kind of synthesize, because you're not going to get that kind of reflection without doing it kind of manually. Because I think if you just store everything in this unified approach that some of the papers use, it's very hard to kind of have those higher level reflections. Yeah. And then there's also different ways of doing it. I think some of the papers focus a lot on trajectories. So it stores like, in order to do this action or this task, I had to do 5 different things. And it stores those as their own like little memory blocks, is how various things were done. And then they use that to reflect on like future ways to do that thing. So there's kind of different things that get stored in memory. It can either be everything you said, it can be like your chain of thought for how to do something, it can be what other people in your environment said. So yeah, there's kind of a lot of inputs to the memory as well. So this is just kind of summarizing what a few different papers do in terms of hybrid memory. So Agent Sims was like a pretty popular one too. They store their long-term memory in like a vector database, and then they retrieve it in episodes. So again, like how you want to structure episodes, what exactly each of these embeddings are. Is it one observation? Is it kind of a sequence of events? They kind of, yeah, we can dive a little bit more into how these episodes are defined, but essentially they have a vector database that stores different chunked representations of the user's memory. And then GITM stands for Ghost in the Minecraft. I don't know why they have T in the acronym, but it does long-term memory, providing stable knowledge. Yeah, so essentially what it does is, it's the goal of this paper is trying to get agents to autonomously take actions in Minecraft. So they also have a process of kind of transferring their short-term memory to long-term memory. And this is more kind of also what I mentioned about it being on how to solve different tasks. So they have, yeah, each memory thing is like, in order to do this, I did XYZ, and they store that as a memory unit. And then the long-term memory is mostly like, this is what worked to do this task and so forth. And then reflection uses a short-term sliding window to capture recent feedback and incorporates persistent long-term storage to retain condensed insights. SCM selectively activates the most relevant long-term knowledge to combine with short-term memory, and Swift Sage employs a small LLM to manage short-term memory for generating intuition and associative thinking. So essentially, I agree that like kind of my descriptions here are kind of high level. I think what would be really what I was mentioning at the beginning of this call is for each of these, they're in the papers themselves, it's kind of handled in like kind of a high level research like way. But yeah, if we can actually come up with like little diagrams or how these could actually be implemented in like a real system, yeah, I think that would be really useful because yeah, theoretically these are interesting approaches, but I think that like kind of little gap is still there, which would be interesting to work on. Yeah, so this is the memory format, as I mentioned. So I think there's a question about, yeah, how are you storing your memory? What are you storing? And then, yeah, this is like the memory structure. So they kind of break it down into structures, formats, and operations. So the formats are essentially natural language embeddings, databases, or structured lists. Natural language is yeah, just kind of store everything that you get. Embeddings, yeah, use embeddings for enhanced retrieval. So memory bank, GitHub, and chat dev all kind of fall in this bucket. Databases, they have SQL-based structured storage. So ChatDB is a paper that essentially gets the LLM to write queries that can retrieve structured memories that have been stored in the database. So maybe think something like, what did I do 5 days ago? Or what did my friend do? Or something like that. So it's like actually kind of the memories are structured in a based off of a timestamp, various attributes, various locations. So that way you can, yeah. I don't know. I don't know what the performance difference is of just storing everything in raw text and performing like a vector search over it versus like trying to structure it and do like a SQL search. Maybe the paper has more, but that's kind of what that's trying to do. Maybe there's some use cases where you really want to be precise and say, these are all the operations or executions that happened in this time window, where a structured SQL query might be more performant than an embedding-based lookup. And then structured lists as well. So it's like an action list for sub goals that are stored in a tree structure. So this was the this is kind of more for the trajectory part of things, right? So this is my goal. These are all of the things I did to achieve my goal, and it's kind of stored in that hierarchy so that that kind of structure is maintained whenever you query. Cool. Okay, and then memory operations. So this is kind of going into, now that I have a format and I have the structure, how am I going to effectively read, write, recompute, shift things from short term to long term? Like I honestly think they're going to be like LLM memory management companies in the future, that all they do is kind of really provide you with like a whole host of ways to store your memory, but like specific to like your agent's goals, right? Like if you think about it, if your agent is kind of like a social agent, it needs to store and remember things differently than if it's like a robotic planning agent or something. And I'd imagine like it'll allow you to provide all of these different options and so forth. So yeah, if anyone's interested, let me know. But yeah, okay, anyway. So memory reading is like memory is extracted based on recency, relevance, and importance. So there's different scoring functions for measuring each of these. And that's kind of used to figure out how important this memory is for a particular query, right? If it's super recent, if it's very relevant to your query, and if it's just an important memory overall. So generative agents is kind of the main paper that proposed this approach. And they also have some functions for like what each of these simp, srel, srec, like those functions are. And you can kind of change the hyperparameters, the alpha, beta, and gamma, based off of like what's the most important. So yeah, we can refer to that for those functions. Most of the papers right now just kind of do relevance, but they're trying to say that recency and importance of the memory are like as important or can be weighted as desired to kind of make this work. And then, yeah, memory operations. The other ones are writing and reflection. So for memory writing, right, the question is how to store duplicate memory and how to remove memory if there's memory overflow. So the successful action sequences related to the same sub-goal are stored in a list, and when it hits a size, it is condensed into a unified plan solution. This is one approach from one paper. There's a few other approaches, right, like on how to actually yeah, if you're having the same, how to condense and write the same thing. Like, yeah, cool. I think the main thing here is like, it doesn't really make sense to have like unique keys or primary keys or anything. It's more, but you also don't want to, let's say you're like actually have an agent that's been running for like a week and it's taking in logs every few minutes or a few seconds or something. Like a real like production agent that's doing a lot of stuff. I think that becomes really important to figure out, right, how to write appropriately, because yeah, you want to synthesize the information and remove things that aren't important, because an LLM obviously is not going to be able to take in like, yeah, logs forever. So being able to write efficiently and effectively is like really important. And then the memory reflection, there's self-summarization. So the agent has the ability to summarize its past experiences into broader insights. The agent generates 3 questions based on recent memories and uses these to obtain relevant information. This is what we're talking about regarding the generative agents paper, right? How it's transferring the short-term memory into long-term memory and kind of having this reflection process. There's a few other papers that are doing it. I think, as I said, the self-summarization one, and then reflection and generative agents and a few others, how like setting up this ability to summarize past experiences. So again, I think there's a huge opportunity here, because all of these papers, right, they have like a kind of maybe in a notebook kind of approach to doing this. But if you think about it, like how are you actually going to scale such a system and make it work properly? To be honest, I'm not sure if anyone is really doing that well. So yeah, could be interesting to dive into. More about self-memory reflection. So there's this self-verification process. So this is essentially, if you think about it, I have a lot of memories, right? I want to use those memories to better decide if my current actions or current plans or things make sense, right? So here, self-verification is using, there's a few approaches, right? One is using GPT-4 to assess whether the current action is sufficient to achieve the desired task. If the task fails, you have a critic, right, that offers feedback by suggesting approaches for completing the task. So that's one approach. I forgot the paper. I can label it later. And then replug is another paper. It uses the LLM as a scoring, uses an LLM as a scoring function to assess the contribution of each document towards reducing the perplexity of the LLM. And the retrieval model parameters are updated by minimizing the KL divergence between the retrieval probability and the LLM scores. Yeah, so essentially here, this is kind of interesting, because I think, as you all know, like RAG is like a very, I think RAG is kind of made it somewhat to the production stage. Agents haven't really made it to the production stage yet. And with RAG being like kind of in prod in some larger companies, it's become a really kind of hotly discussed topic on how to kind of make sure that your retrieval is like as good as possible. And this replug paper, right? They're trying to actually have the retrieval model get tuned based off of the quality of the responses, right? So the retrieval model's parameters are updated by minimizing this scale divergence, which between the retrieval and the LLM scores. So yeah, it has the LLM that scores the contribution of each document, and then it uses that to update the parameters of the model by minimizing the divergence between the retrieval probability and that score that the LLM provided. Yeah, it could be, I don't know, we could read that too. I haven't read it in detail, obviously, but I think it's pretty interesting because otherwise there's always kind of this open question of, sure, we were able to retrieve XYZ documents, but like, which ones are actually the most important? Can we re-rank them somehow for relevance? Which of them are actually contributing to the answer versus not, et cetera, et cetera. And then this one is trying to actually tune the retrieval model. So yeah, I think it could be an interesting paper. And I think we'll also probably spend another meeting separately on just everything retrieval related. Yeah, I think that one has gotten more like production interest already. So it's probably a little more advanced than agents, but I think that's also like a, you know, a lot of approaches for that. Okay, and then so this is, yeah, more last kind of thing on memory. I think there's a few more interesting papers and ways that they're doing reflection. But yeah, we can go through planning first and then maybe come back to it. So planning, as mentioned, there's they break it into two main sections, planning with and without feedback. So without feedback is really take the LLM, it has a goal, it comes up with a plan, and that's it. The with feedback is like when it comes up with a plan, then it evaluates it, it can update the plan. It gets like feedback from the environment, from the human, from a critic, from memory, etc., and it's able to update and improve. Without feedback, is like your general chain of thought, right? This is probably the most prevalent by orders of magnitude. Yeah, you say let it think step by step, etc., and it comes up with a thought, an observation, a plan, and then like I think feedback is like the four main steps of it. So yeah, each of these three chain of thought, zero shot chain of thought and zero shot planners. These are kind of the most popular ones here, and they're all goal-driven decision-making agents. And then after this came out, right, for the sub-goal decomposition, there was multi-path thought, which kind of was on the thought process of, hey, humans kind of have multiple different options before they choose a next action, right? They have some sort of a vetting process of these three options that I could do next, which one am I going to choose? They kind of reflect and so forth, right? So yeah, the self-consistent chain of thought assumes each complex problem has multiple ways of thinking. Tree of thought kind of decomposes chain of thought into a set of tree nodes for each thinking state. And the LLM has to generate evaluations or votes of all of these kind of thoughts, which are stored in the tree nodes. And then it searches them using a BFS or DFS. So yeah, this is kind of, but again, it's like no feedback. It comes up with various options at each stage. It has the LLM kind of vote or generate an evaluation on each of these proposed options. And then it searches through this tree. Yeah, I don't think we've covered tree of thought either. We can probably do that too. And then lastly, SEICAN. So SEICAN, we had someone present on this a while ago from the robotics reading group. It uses kind of a probability from an LLM along with the value function from the kind of policy trajectory that the robot is using. So yeah, it's kind of combining both of those things. Because I think SECAN, if I remember right, it's like giving it a verbal instruction and it needs to come up with the policy to execute the action. Anyway, I don't remember all of the details, but it kind of combines both of those scores. All right, so that is kind of what without feedback looks like. I think it's generally the more standard system used right now. And then you have with feedback, right? So with feedback, there's environmental feedback, human feedback, and model feedback. So React is kind of has feedback in it. So React extends the agent's action space to a collection of actions and language space. And this is why like the reasoning and actions are performed sequentially. When feedback from an action doesn't have the right answer, reasoning will be performed again until obtaining the right answer. So it's kind of this is why like if you use the React agents, you can see that it tries a few times to get the response. It actually has like an evaluation like, oh, did this solve the answer? Yes or no. If it didn't, it tries again. And then at the end, it kind of has a final stage saying, hey, I got the answer. It's still like very basic, I would want to say, but it does have the ability to incorporate feedback. And then, yeah, these other papers, Voyager, Ghost, Depths, kind of take it further in the sense of, in order to be validated, you need to have different kinds of feedback need to be addressed. So I think I added it a little bit here. So there's different types of feedback, right? So for environmental, as I said, yeah, React extends the agent's action space to a collection of actions and language space. Reasoning and actions are performed sequentially, and when the feedback from an action doesn't have the right answer, reasoning will be performed again and again until it is convinced that it has found the right answer. And then Voyager, Ghost, Depths, yeah, I mentioned that. So inner monologue is another paper, and it has a successful execution of subtasks. So these are the three kind of main things that it evaluates on before determining that the task was like a success. Yeah, successful. It has one verification step that the subtask was executed. And then it also has passive and active scene descriptions. So I'm not sure entirely what that means. We might want to read the inner monologue paper. But essentially it has these three things that it gets as environmental feedback before deciding if it was a success or not. And then self-refine is, again, it has like LLM that's used as a generator, a feedback provider, and a refiner. So this kind of also iterates, right? It generates a proposed action. Some other LLM call provides feedback on that. And then based off of that feedback, it refines it. And then there's reflection. So this one, the actor generates the action, the evaluator evaluates, and a summary of past experience is generated by a self-reflective model and stored in memory to improve the actor through past experience. So this is kind of using their memory as a way to also provide feedback, right? So you can think of it like what I was mentioning before. I've done something similar in the past. This is what I've come up with as my current plan. It looks at the memory and says, oh, is this kind of consistent with how I've solved this issue before? Yes or no. And then based off of that, it kind of updates its memory saying, these are things that work and these aren't things that work and so forth. So yeah, that's kind of how environmental feedback works. And then, all right, any thoughts? We can take a little, I think, yeah, this paper goes through a lot, I think, in terms of if you were also to dive into kind of how all of these are implemented across all the papers, I think you'd have a really solid sense of the current landscape of agents. But yeah, anyone have any thoughts or things you want to chat before we go further? All right. Sure, let's keep going. So the action module is also kind of split up, or this paper breaks it down into all of these different pieces. So the target, they say, is the action of any LLM can be one of these three things. It can be a task completion, finish some task. It can be respond to this user or some sort of dialogue interaction, or kind of explore or interact with your environment in some way. So this is what it says are the three possible things an agent can do. And then the action strategy, right, is either it can recollect a memory, it can have some multi-round interaction, do something, hear back, do something, hear back, feedback adjustment, or incorporate external tools. And then the action space can include tools or it can include the agent's self-knowledge. Cool. So the action module overall, it aims to translate the agent's decision into a specific outcome and directly interacts with the environment, determining the agent's effectiveness in completing a task. So the agent action target task completion has three main goals, right? Task completion, dialogue interaction, and environment exploration. So for task completion, again, it kind of references these two papers, Voyager and Ghost in the Minecraft, quite a bit on how to guide agents in exploring. I think Voyager is also in Minecraft. So there's been a lot of papers and kind of getting agents to do various things within the Minecraft environment, because I think it's really a rich data set, easy to kind of program in, has like visual component, it's a good test bed. So Voyager utilizes LLMs to guide agents in exploring and collecting resources to complete tasks in Minecraft, and Ghost in the Minecraft does something similar. And then dialogue interaction, chat dev, I definitely want to read this, is like it conducts dialogues among employees of a dev company and allows them to discuss things, come up with proposals, ideas, etc. Cool. And then the action strategy, yeah. So memory recollection, generative agents maintains a memory stream of dialogues and experiences. And when taking actions, relevant memory snippets are retrieved as conditional inputs for the LLMs to ensure consistent actions. And then multi-round interaction, chat dev encourages agents to act based on their dialogue histories with others. DIRA, I don't know what that stands for, allows the researcher to provide feedback to the agent as it has this multi-round system. MAD sounds for multi-agent dialogue, I believe, or essentially it's like a debate between multiple agents. And it allows them to debate for some time before achieving consensus. And then Hugging GPT proposes a meta-learning approach to train LLMs to generate code snippets and uses these snippets to call an AI model. Yeah, there's like 20 or so papers that this survey cited for multi-round interaction. So could spend a whole time just on that. Yeah, I think there's also Toolformer. There's a lot about tools. We'll spend more time on this part, I think, next meeting. It's, as I said, very dense. Maybe we should have broken this up into just spending one meeting really diving in on all the memory papers, another one on planning, another on action. I mean, I think you could if you're really going to like read all of this relevant papers and kind of come up with implementation, all of those kinds of things. So maybe we can do that in the upcoming weeks. And then this was, and then this was kind of that table that I referenced in the beginning on summarizing the approaches all of these different agent LLMs use, right? So it kind of breaks this up into all the sections we talked about with profile, memory, planning, action, and then LS as learning strategy. And I guess time is like when it came out. So profile, yes, how to design, how to set up that agent role. So one is like handcrafting, two is based on like seeding it, and then three is like based off of a survey of demographic information. Memory, operation, and structure. So operation is just to read and write. And then I guess 2 is like read, write plus reflection. Yeah, so there's like replug. Reflection uses both, and so forth. And then planning, yeah, planning with or without feedback. So you see there's a lot with feedback now. And then the original ones like Merkle, Tool Former, Hugging GPT, Generative Agents, LLM plus P. Some of these, yeah, they didn't actually have any feedback. And then action is, can it use tools or no tools? So I guess depending on the paper, right? Tools or no tools makes sense. And then learning strategy, I don't remember what, one second, I can just double check. Sorry. The learning strategies were, yeah, so there's 3 different learning strategies they decompose it into. One is learning from examples, learning from human feedback, and learning from environment feedback. So those are the options there. Yeah, we'll go into learning more next time too. It's also a lot of content. Yeah, so for learning from example, it's like you can either get human annotations, you can get LLM annotations, and then the environment is, yeah, we'll go into that after. It's a lot of things for how to get agents to learn too. Okay, cool. I think that is, oh, and then yeah, this is learning strategy. It just kind of breaks it down into different things. And it's saying, yeah. So that's it for this meeting. In terms of, there's still a lot more that we need to cover on this paper, but I really think we could just go back. I'm actually pretty intrigued by memory. I think
This is what you do between midnight and 5 a.m.
me,
Yeah, you just go research memory.
I would be happy to, but
Is
no.
your passion project?
I think it would be real. I genuinely think like we will soon see some like LLM memory companies because I don't think those exist yet. And I think it's conceptually very different than like traditional memory, right? Because if you think about all of these approaches, um, I don't even think standard, okay, so I mean, traditional SQL, NoSQL, are kind of out of the
Oh,
box.
they don't work.
They're not going to work. And then I think even vector databases are also not that great, right? Because like, I feel like there's going to be serious advancements on top
You
of
have
them
the
in the
information
next.
bottleneck. If you represent a transformer model as a graph, and you try to pick up one embedding space to the next embedding space, the graph's traversal is bottlenecked by the information.
Yeah, yeah. I mean, at the very least, right? Like, yeah, I mean, I think we're seeing those issues with RAG already, right? Like just doing kind of semantic search plus re-ranking isn't going to be enough. And I think you can see it already by how these papers are proposing some of this, right? In the sense that, yeah, short and long term, right? If you wanted to actually do the reflection and come up with higher level reasoning based off of things, which is what humans do, right? Um, that's not going to work
We
with
need
just
an
like
entire new model. But the other bottleneck is like is about inference time in QPS. Imagine if you have lots of these processes, right? Not only you carry the error of each prompt, you also carry the inference time. So then like you take like 1 minute to come up with like a like to go through the chain to come to the result. Imagine.
Mhm. Yeah, yeah. I mean, I think those will all be problems that need to be solved with this too. But I really think it's just that we haven't really seen production grade agents that do anything non-trivial, right? Like all the kind of React agent can do right now is I tell it, hey, kind of like, can you use this tool? And it will be like, do I have this tool? Yes, I have this tool. Can I use this tool? Okay, I use the tool. That's like its entire life cycle, right? I mean, we can also dive deeper into the Minecraft papers. I think those ones are kind of building on top of that more. But my whole point is that, yeah, I mean, I think this is definitely, we just haven't seen production ready agents that have to do anything non-trivial, and that's why I think these like memory solutions just aren't out there yet, because it hasn't, people haven't, the like industry hasn't gotten to that stage yet. So yeah, I think yeah, I would probably do another discussion just deep diving into each of these memory approaches. And then obviously planning and action also have a whole plethora of papers to go through too. Um, yeah,
So let
I think within this one, the two ones is, yeah, Voyager and Ghost in Minecraft were discussed quite a bit, as well as chat dev. So those might be three things. Um, yeah, we can. I also think we should not be doing like one paper a week. Like if we want to do like a memory one, I'll
I would
go through.
love you to talk about the ghost one.
Have you read it or?
No,
Yes.
but like I find it interesting because like it's
Mm.
very challenging to build these environments. As you can see, DeepMind has their environment. Some people use like Gym, some people use Mujoko, and these people use Minecraft. It's kind of creative.
Yeah, no, no, I think there's a decent amount of papers in Minecraft now. Like it's a, as I was saying, right? It's like a really good test bed for agents, and because you can ask it to like go build a house, or you can ask it to
Now
go.
there's more to it. How you structure the data and how you get the data from the environment and interact with the environment. That's the
Mhm,
most important part.
mhm, mhm. Yeah, yeah, yeah. Okay, yeah, we should definitely cover those, and maybe, try to play around with it too. Because I think if you're trying to test different things, it seems like a great. Even generative agents was in some sort of a like a simulated world. I think that was in
Also,
Sims.
torch libraries like stable baselines has been gaining popularity.
Sorry,
Like there's different torch libraries, like stable baselines is one that's now pretty popular.
what does it do?
Well, it comprises lots of these algorithms,
Got
you know,
it.
the building blocks.
Mm-hmm. Nice. Okay. Well, I think we have a lot of things to cover in the next few weeks. I think first we'll try to get through the rest of this paper. So um, I think Akash will be taking like the next few sections, and then after that we can kind of dive deeper into each of them. Um, I think we also have this idea of like turning all of this into a blog post. Um,
Are you guys coming for near Ips in New Orleans?
I am not.
Uh,
Are you?
maybe we could all meet up there. It would be so cool.
um, sure.
Sure.
Yeah, we can try to chat about it offline. Cool. I will end the recording.